Hello, everyone. Welcome to the video. And the last time we talked about the derivation of the Black-Scholes equation, and I plan to talk about how to solve the Black-Scholes equation. But when I try to get some notes down for the Black-Scholes equation, I noticed probably it's less necessary to talk about the geometric Brownian model for the stock price. First reason, because this is a very important assumption for the Black-Scholes equation. And the second, the idea of how to solve this stochastic differential equation will help we understand how to solve the Black-Scholes equation. So now let's start. So same format. I will put everything in a table and the number each equation. So usually if you start look at the geometric Brownian motion model for stock price, you will see the equation number 3. I am a person started the traditional differential equation. So I try to, that's the reason I add a step 1 and a 2. So the step 1, the basic equation 1, basically is the standard format for stochastic differential equation used in physics. And it's basically is a standard form and add a so-called Gaussian white noise added to a standard differential equation. And you can notice there's two parameters here. One is mu, one is delta. The mu is a so-called percentage drift, and the delta is the percentage of volatility. So these two are constants in this situation. And if we have after we have the equation number 1, and I did some searching and I found that there's a relationship between the Wheeler process, which Brownian motion, has a relationship between the so-called Gaussian white noise and the Brownian motion process. They have this relationship. So we, according to the 1 and the 2, we will get the equation 3. I mean, the whole reason I do this because I'm familiar with the form equation 1 and add this, multiply both sides by the dt, I will get equation 3. So most time, a lot of study and lecture will start from the equation 3. So I just want to show how it comes to equation 3. And I assume it's because the stochastic process is continuous but non-differential. So we, instead of doing this, we have to use this form, just directly use ds. So this will be the so-called geometric Brownian motion model for the stock price. And there's two parts, as we mentioned in last video. There's a drift part and the volatility part. The mu is, again, so-called percentage of drift. The delta is a percentage of volatility. I think people are familiar with that. So after we got the equation 3, we can see this equation itself is a stochastic differential equation. So in order to solve to get the stock price, we have to solve the equation to get an expression for the stock price if we assume the stock price follow this geometric Brownian motion model. So now let's look at step 4. And step 4 is a very good idea to solve this simple stochastic differential equation. So thus the transformation is done. So basically we let y equal to log of the stock price. So if this formula hold, and we know that the further y with respect to s is 1 over s and some other relationship. So basically the idea here, because this one's simple, you can easily look at it. The idea here is you have to solve a lot of stochastic differential equation or whatever partial differential equation. Using brute force to solve it is very hard. So you have to, usually, there's some, most time in a lot of areas, there's some kind of transformation to make it into a simple form. Then people can solve it. Which actually in my business, in my engineering area, same thing. We have a partial differential equation. It's very hard to solve. A smart guy 100 years ago come out transformation, make it into an easier form so people can solve it. So this idea is called transformation. This idea will be used in how to solve the Black-Scholes equation also. So, but here it's simple, okay? Now, simple transformation from the a to the lemma, we already know that if something is a function of the s and the t, following the a to the lemma, we can easily get this equation. So basically, it also has a deterministic part and a stochastic part. The dy has these two parts. You have to solve the dy, and because we already we already know the relationship between y and s, so we just replace the y and s using replace 4 in the equation 5. So we will get dy equal to this plus this part. And we further simplify this equation. We got a simpler form, the dy equal to mu minus half of del square dt plus del dw. And how to solve this dy, and usually we just do a integration. So we can go to the step 8. So step 8, we just do an integration of y. So on the left side of the equation, we got the y. On the right side of the equation, we got a two part of integration. One is the so-called deterministic part, and the other is the stochastic part. So because this deterministic part is easy, because usually we integration of this is simply just equal to y0 plus, because this has nothing to do with time, because the mu minus half of delta square, and multiplied by t minus 0. So this is the first part. We got y0 plus this. And for the second part, and the integration of the delta by multiplied by dw from 0 to t, the integration of this part is equal to delta multiplied by wt minus w0. And I use equation 7 to prove this relationship. And we already know for the Wiener process, and the w0 is equal to 0, so we just know, so we got this form. So basically y equal to y0 plus mu minus delta by 2 parentheses multiplied by t plus delta wt. So this part is the deterministic part, this part is the stochastic part. After we got this part, we can observe the solution of y. We can notice because we know the Wiener's process at any time t is a normal distribution. So basically, from this solution of y in equation 8, we can see that yt, which is log of s, is normal at time t is a normal distribution, which means y0 plus mu minus delta squared by 2 parentheses multiplied by t, and its variance is delta squared multiplied by t. So we can see that yt is a normal distribution. Now, because we know that yt is equal to log s, s is e power of yt, so we will know the stock price at time t is not normally distributed in this form. This is his mean, this is variance. So the equation 10 shows that we are saying, okay, the stock price at time t is a not normal distribution. That's how it comes from. So the equation 10 demonstrated that part. So then let's go back to the solution of s, because we already got a y equal to this, and we know s is just e power of y. So we got the solution of s, which is the stock price. So basically, the stock price is related to the stock price at time 0 and exponential e power of this part and this part. So from equation 11, we will get the stock price expression. So in order to, we can see that this stock price is a stochastic process at any given this equation. So that means if we know stochastic stock price original price, and we know the percentage drift, and we know the percentage volatility, and we can pretty much simulate a stock price. So this video is basically, in summary, we're just talking about there's a few things I want to, in summary, I want to talk about it. So first, the geometric Brownian model for stock price itself is a stochastic differential equation, and in order to solve this, to get the expression of stock price, we did a transformation, and this is the key step. And also we use Ito's-Nama, and this is another key important. And also during the process solve it, we know that the one important assumption for stock price at time t is the stock price is not normal distribution. This is what people are talking about, why the stock price at time t is not normal distribution. And after we got the expression for the stock price, if we know the percentage drift, and if we know the percentage of volatility, we can simulate a lot of the stock price. That's pretty much the summary of this video. And in the next video, we will start to talk about the how to solve the Black-Scholes equation. And hope you will learn something from this video, and hope to see you in the next video. Thank you. Bye.